Yes, so please, good morning, everyone. Yes, so good morning. Sorry about that. Right, so we want to start the DCD now, right? And this is strictly for midterm, right? It's not for anything else. So please prepare like we're preparing like we're going for midterm. And how we'll do this is that since we don't have a lot of time now, I will do it in two parts, right? One maybe 30 minutes or 25 minutes, and then the next one we'll use to solve a question, like a couple of questions, so that we can get the concept really down, right? Beautiful. Okay. Okay, cool. So we'll start off first with the K maps, right? We'll do some revision on the K maps, and then we'll look at the state diagram, right? And then we'll look at the recommended steps, look at the architecture. We'll just basically look at everything except an example. You understand? So please let's begin. And yes, please forward it to your computer friends if you have any, right? Because it's a general course for everyone. So the more that people get excellent marks, the better. Okay. Yes, so the K map, right? So the fact is that why is K map necessary? That's the first question, right? The kernel map is always necessary because with your normal Boolean like minimization, it doesn't always result in the best minimal result, right? Or minimal value, right? If you want to implement a certain Boolean expression or Boolean function, and then it is not the most minimum, there's a waste of gates, and that is not effective, right? There's a waste of gates, there's waste of time because gates have propagation time, right? So you cause delays in the circuit. That is unnecessary. Yes, sir. So if we want to start with the K map right now, kernel map effect. Right. So to draw that, when you're given a certain function, so the function I have here is a very, very simple one. A complement B C complement plus A B complement C complement plus A B complement C plus A B C complement. You understand? We could solve this the usual way, but let's go with the kernel map so that you can get a handle of it. So to find the kernel map for this, what you have to do is first you have to decide, or like you have to determine the number of distinct variables or unique variables in your system. Right now we see that we have A, we have B, and we have C, right? We don't have any other type of variable, so our n is equal to 3, right? We need a 3-bit kernel map. So now let's go ahead and do it. First of all, if you remember, we have this. I'm drawing our thing, right? So we have A here, and then we have BC here. Then the A is 0, 1, and then this is A bar A. And then keep in mind, one important thing is that as you arrange them next to each other, they should toggle. Just one bit should be toggling at a time. That's why it's like this. It's not in any other way. We just want one bit to toggle at a time. So 0, 0, 0, 1, then 1, 0, then 1, 1. Sorry, 1, 1. That's a difficulty with this, right? The writing part is quite sensitive. At 1, 1, and then 1, 0. You understand? This is how it would become. And we can draw three lines. And then we can describe this as BC, 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 BC. But B bar, C bar, B bar. That's perfect. This is how we would place it, right? Now, when you look at it, you can be able to tell. Or so first way is that you would just look at it and then you just fit your one values inside. You see, this is a sum of products, right? That means that this one should give you 1. This one should give you 1. We could draw a truth table for this, but it's not necessary. This one too will give you 1, and this term will also result in a certain 1. You understand? So if you look at A bar is here. Right, then we look for B and C bar. This is it, and then we put 1 at the intersection because A bar is here, B bar, C is here, so you place it here. The second one is that you can look at the terms and then write out min terms for them, right? So A bar B, C is equal to, like A bar, B, C bar will be equal to 0, 1, 0. And 0, 1, 0 is what? Is a 2. Right? And if you look at your table, I don't know whether you remember this, but this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. So 2. I missed the 2. 1, 2, 3. Okay. What's happening? You're supposed to start from 1. Sorry, you're supposed to start from 1, right? 1, 2, whatever, right? It's supposed to start from. Oh. I don't know why it's not giving us. Well, let's move on, right? So A, B, C. You have A, then you have B bar, C bar, 1 here, right? So you have A, B bar, C. You have A, B bar, C, also resulting here, and A, B, C, A, B, C. You have it resulting in something like this, right? So now you've gotten your entries into your table, and what you have to do is you have to minimize now, right? So the thing about it is that you have to circle. I don't know whether you remember this, right? You have to circle you have to group ones and then circle them, right? And it is the circles that you are going to like find your implicants and primary implicants and whatever you find, and then you write down your minimized expression. You understand? Okay. Oh, sorry. So you have 1 here, right? Yeah, and one thing I didn't mention was also that the ones, you can't just circle them in any random order or number, right? You're supposed to circle them in increasing multiples of 2. So if you have 0 ones, you can circle them. You have 1 ones, you can circle them. If you have 2, if you have 4, if you have 8, if you have 16, right, and it goes on in that order, right, you can circle any number of them as long as they're either 1, 2, 4, 8, or 16. You understand? So that's why we don't just circle it anyway, right? So we'd have this, and then we'd circle the one just to be like that, right? We could have also done it like this. No harm in doing that, right? So now we have 3 different implicants. The first one, so now what we have to look for is that we have to look for the one that doesn't change, right? So which one of the values doesn't change, and that's what becomes our value. So let's put this as I, let's put this one as I, and let's put the last one as I. One curious thing, right? I would give you these two, right? Now what is giving you is that A doesn't change for any of them, right? But C changes. C changes from C bar to C, and then B bar remains the same. So what we'll have is that we'll have a product of the two things that doesn't change, A, B bar. Now I would give you this one too, right? What changes in it? A would change from A to A bar, and then B bar and C2 doesn't change. Understand? No, with this one, it is ineffective. Like it is. Oh, I'm looking for a different word, right? It becomes redundant, right? It makes your circuit redundant because whenever you circle every one that you take out of the equation, and what happens is that you get like that same like one. You have 3 different values for it. So if you find right now, if you find the I, right, we find the Carnot map representation of it, that you have A, B, C, but we don't want that because it just makes the circuit complex. So we can extend this to this, and then we're circling 2 A's now. So right now we don't have A, B, C, but we have something that changes. It's because you're moving from one cell to another, right? So what is actually changing here? Because A won't change, and then this one B will change from B bar to B, so we have AC. You understand? And then you just place it, you add all of them. I really hope this is the answer. Yeah, this is the answer. So yes, we can move on. Right now we've been able to find it. So it's the same concept for 5 input K map or whatever. Yes, and one important thing is that when you get above 5 values, it's better to use Kimaplexy, right? That it just makes sense. Right? And keep in mind that your equation can also come in like this form. This is just for revision. It won't come in there. We know what he said will come, right? So this is just for maybe exam or something that you're looking at it. right? This one too can come. This one are your min terms. So this one to same thing. You draw your table. This is x. This is y z. You have 0 1 0 0 0 1 1 1 and 1 0, right? And with this one, you'll be able to. So this one is 0. This one is 1. This one is 2. This one is 3, 4, 5, 6, 7. Right? You write it like this, and then 3. You put 1 here. 4. You put 1 here. 6. You put 1 here, and 7. You put 1 here. Then you draw your what do you call it? Your circles around them. This is I, and this is I. So then what is changing here, right? This one Y and Z, they don't change. They don't do anything, right? And then the second one I, what is actually changing? X doesn't change, right? It is 002. It's 102 002. So it is the y that will actually change. So the z remains the same, right? Z bar, and this becomes your final solution. It can also come in this form, right? Sorry, I'm rushing here. We need to hurry up. Right? And as I said, yes, the state diagram. Now, important fact to know about the state diagram. Right. First of all, the state diagram, each state is represented by a circle with the state's binary value in it. Right. So if you want to represent the very first theta, we do like this. Right. That's how we do it. Any state is just represented by a circle with the state value in it. Secondly, right, clock triggered transitions between states, right? Because this is sequential circuit design. States change with triggered clocks or clock triggering, whether edge or leveled, right? So what you have to do is that you would like indicate changes or transitions with directed lines, we call them paths, right? So for example, let's say that in your circuit, you change from 0 to a 1, right? When the input is like you change from 0 to 1 when your input is, let's say, 4. No, it's not possible. When your input is 0, right? Something like this, you say that input is equal to 0, something like this, right? You've directed it, so you change from 0. There is where you're starting from to 1, directed path, and then you place the input beside it. So this is how we also represent it, right? That's how we do it. From a previous state to a current state, use a directed path with the value beside it. Excellent. Right. Now, each line, right, originates at a present state and terminates at a next state. So that's what we just did here, right? Starting from here and here. It's very, very important that you know this. And the last one is that when you have a present state and this is your next state, and you have a straight line in between them, it is your input slash output. Most of the time, will not have need for the output. We just want the state to change, and that one we'll just put the input there, right? Like the example we did on Monday, right? We have no need for output, so the output is not necessary. That one we'll just place E is equal to 0 here, comma R is equal to 0. Like, you understand, there's no need for output. But if there was you put a slash here, and then whatever output you need, let's say Y is equal to 1, something like this. You do it like this. You understand? Now that's how a state diagram is drawn, and you need to be very, very careful, because like if there's only one questioner, there will be a lot of marks on specific things, and this might just be one of them. Now let's talk about architecture, right? You remember when we're doing the example remember that we talked about architecture, but it wasn't, maybe you didn't know what it was, or maybe you knew, right? Either way, right, I'm going to go over it. Right, we have the Mealy architecture and we have the Moore architecture. I don't know whether I remember. They're not really called architecture. They are called. So yes, so sorry. Right, we have the two, and they're different ways of like basically expressing anything. There's just one major difference between them, right? So for the Mealy architecture, what you have is that you have a combinational circuit here. Maybe you have a combinational circuit doing some curious thing, right? And then you have a state register down here. So usually it's a state register or your flip-flops. Like they've given you a number of flip-flops and you want to represent them. That's where you place them. You understand? That's basically what is happening. So your output, this is your output, right, of your combinational circuit. You have some inputs, and then you also have some inputs coming from, let's say this is the output part of your state register or flip-flop. Sorry. Right. This is your output part. That means that you would do it like this. The output is feeding its own You're not connected, please. Yes. Okay. The output is feeding its own thing, right? And then keep in mind that because the flip flop, you need to bring a clock. This is a clock, right? That's basically what is happening, right? When your combinational output, this is input, right? When your combinational circuit is up, your state register is down. Your outputs of your state register of flip flops are feeding your combinational circuit. Right? That's what is happening over here, right? With your with your Moore circuit. And so with when we talk about the two different architectures, and should I it will take a lot of time, right? But basically when we talk about the two different architectures, and we have some output here, right? We have some output combinational circuit here, right? What happens is that your input, your output of your state register or flip flop also go as inputs to this one, right? And then your inputs also come here, right? There'll be a question we'll solve that this will become necessary, right? That's just what's actually happening in your Mealy architecture, and your output values are here. In your Moore architecture, what happens is that there's no input, like it just relies on the past, right? It doesn't rely on current input, just your past, right? So we can have an architecture like that, right? This is basically your Moore architecture. That's what's happening. Your inputs only feed your combinational circuit, which produces an output, and your state register or your flip flops also manipulate it to also give the combinational circuit some values. Right now, that's what's happening, and your state register will feed an output combinational circuit, which will give you your output. But when it comes to your Moore circuit, your inputs are also part, and then it feeds your output combinational circuit. Right? Any questions? No, not yet. Excellent. So we can continue. And that's basically it. When we talk about architecture, keep that in mind. It is very important. Right. Beautiful. What is next? Right. So we've talked about the kernel mobs and things. So now let's actually go into the business of the day, right? How to design a sequential circuit when given a question, or what do you call it? When given a question or a story, as he's going to give us in our midterm. You understand? So let's begin. Right. So the first step is that from your word description, sorry, that was a nasty one. Okay. First one, from your word description, or from your question, or from your story, right? Derive a state diagram. Derive a state diagram, or like produce a state diagram, draw a state diagram, whatever you would want to use, right? So from a word description, the question we're about to solve was this, right? A sequential circuit has 3 flip-flops. So we'll read the question, and from this, right, we'll be able to determine a state diagram. Or if sometimes they will give us a state diagram. That's what happened in the same one, right? They give us a state diagram. So if they don't give it to you, you know how to draw it. I already showed you. So what's an example of a question that, or an example of a state diagram that you can look at, right? There's something like this, right? Let's say that you want your circuit to move from state 0 0 to 1 1, and then from 1 1 it moves to 1 0, and from 1 0 it moves to 0 1, something like this, right? What you do is that, and they are one directional, they don't go back, they just follow sort of a cycle. What you have to do is that you have to do this, right? Your 0 0 goes to 1 1 when probably your input is 1, and then your output is like, your input is 1 and maybe your output also becomes 0, something like this. And from 1 1 it moves to this one, right? So it is basically, where do we start from, where do we end, and what inputs are determining that factor. You understand? So from 1 1 moves to this one, and from this one to it moves to this. You understand? It can be like this. Or maybe from 0 1 you want it to loop itself, you want it to be at 0 1 forever, then you just do like this. Right, you just let it connect to itself. So whenever it's in 0 1, it just keeps looping itself. I hope you understand. If you don't, then as we discuss the question, as we look at the question, you would get it. So please hold on if you don't understand. But I know you do understand, Charlie. You guys are wild people. So I know you do understand. Excellent. Now the second one is that reduce the number of states. Right. One important thing that you would have to remember is that, like, it's something that, like, you can forget about it if you're not given. So for this question, For this particular question here, you realize that they told us it has 3 flip-flops, right? They told us it has 3 flip-flops. But the thing is that what if you're not giving a number of flip-flops to you, you're just giving the number of states or the state description. What you do is that you do this. So for a state machine with, let's say, n states, right? It has n states. Let's say it has like 12 or 11 states or something, meaning that it has 12 individual states. Meaning to move from 00 to 01, like the number of circles you see in your state diagram here is n. That's what you're saying, right? What that means is that we'll need, how many bits will we need to represent it, right? So that's the question we need to ask ourselves. How many bits will we need to represent any states? So you already know how to work it out, right? It will help you determine the number of states that each one will, like, each you will need for each. You understand? Yes. So when you found the answer for this one, that's the number of like flip-flops or the number of bits of your state register that you will need. You understand? That's just basically what is happening here. So an example is, given 12 states, given a question with 12 states, how do we find the number of states that, so not the number of states, the number of flip-flops or then the number of bits of our state register? What we'll do is that we'll find log 10 of this of 12, right? And that gives us a decimal, but we'll round it upwards, right? Round it up, because we can always have unused states. If our state machine or our circuit, like, it doesn't use some states, that's fine. Rather than you don't have some states at all, you understand? We always round up. Keep that in mind. We always round up. Excellent. This one you would get like 3 point something, you round it up to 4. Right? It means that we need 4 flip-flops or 4 bits of our state register. Okay, we can move on now. Right. So now when you're done reducing your states, right, what you do is that you obtain your state table. Now that's basically like the part that is most difficult, right? So if you go and sit down, your state diagram is very, very easy to find, right? Your find the number of flip-flops is very, very easy to find, but the most, I don't see challenging, because everything is just easy over here, right? So if you're not doing DCD and you chance upon this video, please do DCD. It's very good. It's very good for your health. Right. The step 4 is step 3, right? Step 3 is find your state table. Now, in the state table, we are coming to break it up into a couple of parts. We'll break it up into 4 different parts. The first part is that we'll find our next state table. Right? Find our next state table. What that means is that so the next state table, right, why I've called it that is that it's a table that tells you what the current state is and what the next state is, right? So like with this one, it depends on what kind of circuit you get. So let's say that you have a current state, right, in your state diagram. I really want an example to work with this so that it makes sense, but if it doesn't, I just try and follow along. It will all make sense, right? So you see, you have the next state, so that means that you have some current state. You have some current state. You have some current state over here, and then you have the next state. So let's use the previous example, right? You have 0 0 to move to 1 1 to move to 0 1 to move to 1 0, right? And we want 0 1 0 0 to move to 1 1, and then we want your 1 1 to move to, this one is an arrow, please, and then we want your 1 0 to move to this one. So with this one, it is 2 bits. So if it is 2 bits, if it is 2 bits, we can say current state 1 and then current state like 0. The next state 1, next state 0. Right? And then we'll have 0 0, right? 1 0, 1 1, and then 0 1. You understand? You can do it anyway, right? The order shouldn't be important. Right? So now from 0 0, where do we move to? So you can see that from 0 0 we move to 1 1. So the next state you want is 1 1. That's why we say it's the next state table. Right? Now from 1 0, where do we move to? From 1 0, we want to move to 0 1. And then from 1 1, we want to move to where? 1 0. And then from 0 1, like from 0 1, we move to where 0 1, we don't do anything. So it's a don't care. Right? So that's the like the indication we are going to use, right? It's a don't care. So now this is basically our first table. Very, very easy to find, like deceptively simple, right? It's very, very simple. Nothing else to work with. There's some caveats with this, right? When you get one leading to 2 different states, right, based on the inputs. But we'll talk about that when we actually see a question. Right? It is very, very important that we work plenty questions and then we have this on our head. in our head, right? Now the next thing we find in our search for our state table is that we'll find our like next state excitation table. You understand? Now you see, we want to determine what kind of flip-flop inputs that will need to excite the proper flip-flop transition. This just with this one, you will need to know one, like the type of flip-flop you want to use, type of flip-flop used. And the second one is that you will need to know the truth table for that flip-flop, and then you need to know the excitation table. Sorry about that. We need to know the excitation table for that flip-flop. Excellent. So with this four ones, then you'll be able to determine your second one. And the third one is a breeze. That's the final step, right? It's a breeze. So what type of flip-flop are you using? You see, there are only four types of flip-flops that we've done that we can be used. The set and reset flip-flop, the Jack and Kilby flip-flop, the toggle flip-flop, and the data flip-flop. There are four. So if you really know in your heart that Charlie, it will trip you up, chew the truth tables and then chew the excitation. I simplified the excitation table so you would see it very soon. But if you know you can't, Charlie, chew it and let's move. You understand? So I don't know whether I should draw it here or okay, sure, let's move, right? For the JK flip, so that I remember it myself, right? For the JK flip flop, we have the next state being, if it is 0 0 0 1, 1 0 and 1 1, right? But if it's 0 0, we maintain the states, and these are all NAND. Keep in mind that these are all NAND flip-flops. That's why it's like this. If it is no, it becomes something else. But this is just a revision, so let's not go into all that, right? So now, so 0 0, it is Q0. For 0 1, it is 0, right? It follows the G, and for 0 1, it is 0. For 1 0, it is 1, and for this one, it is toggle. You understand? It toggles. For the SR, so in some design questions I've seen, you will need to like decide your own flip-flop that you want to use, right? And the simpler the better. So Charlie, go for data. Data is the easiest that you would so that you would right. For please, I'm coming here. Please first. There's something. Yes, so please, you're welcome back here. Please, you have to forgive us with the noise, and we are trying our best with under these conditions. With so now for the SL, you have the same one being modeled over here. Now this one too follows the S. So sorry, if I remember correctly, right? We hope I remember correctly. Yes. So 0, then there's 1, and this one is an invalid. Right? It doesn't count. Now for your D flip flop 0 1, as I said, this one is the simplest, right? 0 1. Your toggle. So for your toggle, you have it as 0 1, and then you have it as 0 and then a toggle. Whenever it's 1, it toggles. Basically, very simple to remember. You understand? So K follows the G, SR follows the S, D follows themselves, and then T follows it. You understand? Now this is the truth table for them. Very easy to remember. You need this in your head. So as long as like you sit down, or just write this down on your table or something, so that you can have it in your mind. And you have an excitation table. As I said, I've simplified the excitation table, right? So that it's just one table. You don't have to keep 4 tables in your head. Right? So we have the current state, we have the next state, right? Now we have SR, we have JK, and then we have D, and then we have the T. You understand? So now this is, let me draw some lines. Okay, back to it. Okay, so yeah, so whatever you need, then you just pick it out. Right? If you need the SR, just take 1 column, 2 columns, 3 columns, and 4. The first, second, third, and fourth columns. If you need JK, pick this one, pick this one, pick J, and pick K. If you need a D, pick qn plus 1 and pick d. If you need a t, that's what you're doing. So there's just one table you're trying to keep in mind, and it makes it simpler. 0 0 0 1 1 0 and 1 1. Yes, and you have for the SR, you have 0x. So I think that after this video is done, I'll take pictures, I'll write them down, take pictures, and then I would put them in the link of the video so you can download them and then have them like on your fingertips when you need them. Right? You have 0 1 and then you have XO. Right? For the JK, you have 0x 1 x x1 and then x0. Right? Now for the D, as I said, the D follows, so 0 1 0 1, it will go 0 1 1 0. And this is your excitation table for all of them. So if you want to write them down, you can pause the video and then write them down right now. Right now, as I said, now we are just coming to find the final one. Right, that's the what we want, the state diagram itself, the state table itself, sorry, and that's what you're about to find. And what that involves is that we'll take the two tables that we worked with earlier, right? And then we'll just we'll take the two tables that we worked with, and then we'll combine the next state table with the excitation table of that particular flip-flop we want, right, to form the desired state table. You get? So now this is the structure for the state table. As I said, this is just a revision here. I'll try and finish this up this video so that we can have an example to our names and then we can work with it, right? So we have flip-flop inputs. So we're assuming that for this example you're using JK flip-flop because that's the most common, right? It's the most common. Right. So for the current state, we have Q, Qn of this current level, and we have Q, the current state. When we say T, that means we are current is this particular time, and when you say Qn and T plus 1, that means that that means that we are talking about the same one. Oh, sorry. Let's reduce this so that it's simplified now. Right, beautiful. So we have 1 0 1 0. Sorry. Yes. Please everybody say welcome to Caleb. I'm a Wowo. Right. Very shy boy. Say hi to him when you see him in class. Yes. So the flip-flop inputs, right? The flip-flop inputs. So let's say you're using JK flip-flop. That means that for the first one we have a J input, we have a K input. If it's D flip-flop, we only have one input. And let's say you're using 2. Right? If you use 3, it will become J2 K2, J1 K1, J0 K0. Right? It depends on what you are using. So back to it. So now we have a current state, we have our next state, we have our flip-flop inputs, and then we have our flip-flop inputs too. Yes, back to it. Yes, so that's what you do. So right now, as I said, we don't really have examples. So this is the structure of the table. So you can put it down, and then I wish we had an example that we could be working with, but looking at the time constraints, right? So we have our current state. So if you remember, we did this one. Right, so we had this, right? So if you look at the first table that we did the current state and the next state table. So that's what we'll do over here, right? We'll just fill it in and then we'll place it over here, you understand? And then we'll put our next state over here, and then we use the excitation table to determine what it should be. How we do is that, right, how we do that is that we look at the current state and we look at the next state. Then we'll say that what is the input, what is the J and K input that will give us our next state, you understand? What are the inputs to J and K that will give us Q1 and then Q0 of our next state, understand? And that's what we do. Excellent. So that's how we find. As I said, if it's going over your head, please don't worry. We would yes, so if it's going ahead, we would solve an example later in the day. So please just watch the two videos together. That's why I'm apologizing plain. I'm so sorry. If it's also SRR, place SR there. If it's DR, also place D there, you understand? And this, if you remember what I said, it's based on the number of bits of your your this thing of your state. You understand? So you take the state, you find log 10. Hey, have I said 10 all this time? I mean saying 10. Log 2, please, log 2. Yes, log 2 n, where 2 n is the number of your state. So yes, 2 2 2 2 2. I'm sure somebody said it, but I didn't come to. You understand? Excellent. So now we've been able to find our state table. So the next step is okay. Yes, so the next step is that we'll take the what do you call it? Our next state in our output. So let's say that we have two next states. We had J1. So we had four: J1, K1, J0, and then K0. Right. So what we'll do is that we'll find a kernel map representation of them. That's why we taught you the kernel maps, right? You find a kernel map representation of J1, K1, J0, and then K0, right? And then we use to find the expression, and then we'll draw a combinational circuit for it. It's very, very simple. If you have any questions, please let me know. When we come back from our class, I would get right into it. So DCD people, please watch these two videos together. Go and look for part 1 and part 2. And thank you so much for being here with us. And as usual, we have to thank the people who gave up their rooms once again, right? Caleb Akanseba Akani, and then UC Hayford, right? I don't